We now discuss the power analysis attacks. We will cover both simple power analysis and differential power analysis. In simple power analysis, the attacker attempts to visually examine the system's current or power waveforms during execution in order to discover information about the data or operation. This is based on the fact that the system will consume different amount of power when perform different operations, or the same operation with different input data. The power and the current traces can be obtained by oscilloscopes, high-frequency components that do not reflect the data-induced power variations can also be filtered out. For devices such as smart card, the power and the current information can be read directly from the terminals. The oscilloscopes and other equipment to measure power or current are widely used in the design, testing, and the debugging of the systems. They are relatively inexpensive and they can provide a pretty high precision of the measurement. This is the pseudocode of the square and the multiply algorithm that we have learned last week. It is one of the most efficient ways to compute the value of a to the power e mod n. Remember that this multiplication operation will only be executed when k sub I equals to 1. This multiplication is a non-trivial operation, and its data-dependent execution variation can be observed through set channels such as power, current, and timing. We have mentioned that this might lead to side channel attacks that can reveal the value of the secret key. Now we will see how this can happen. Square is a special case of multiplication, since it is a very popular operation in signal processing and other applications. Many systems have special implementation of square that is normally more efficient than multiplication. This results in measurable, shorter time and less power consumption to compute b squared than a times b. From this simplified power trace, we can distinguish the square and multiply operations. The x-axis is time, the y-axis can be seen as either the power or delay. Square is short, and the tall bars are multiplication. Now recall that multiplication is only executed when the key value is 1. We can easily retrieve the key value from this trace. First, the tall bars corresponds to the power or current for multiplication. Therefore, these bars and the shorter square bars immediately in front of them are related to logical ones in the secret key. The other ones are only square operations that corresponds to logical 0 in the key. And this is a way how we can retrieve the secret key that has been used to compute this modular exponentiation. Simple power analysis not only can reveal the key data value, it can also leak information such as which round of the encryption is performed. However, as we have said earlier today, simple power analysis relies on the visible information from the power or current traces. Without using analyzing tools, large number of traces do not help much. This also implies that the precision of this side channel information should be relatively high. To deduce secret data about the crypto algorithm from the very limited visual evidence in the power and current traces, a good understanding of the crypto algorithm and its hardware-software implementation will be critical to the success of a simple power analysis. Simple power analysis attacks are non-invasive. because the attackers will only collect the power and the current traces during system's normal execution. They do not leave much evidence of the attacking either. However, it is possible to combine power analysis attacks with other passive attacks. For example, if the attackers can control the input signals, they can have the system running with input data of their choice to obtain or verify the deduced information from power trace. A more effective way is to use fault injection methods so the system will run at abnormal mode and the power or current traces may leak more valuable information. Because of the simplicity of simple power analysis, there are many countermeasures that can effectively prevent simple power analysis attacks with little or no cost. Therefore, advanced power analysis methods known as differential power analysis has been proposed. Differential power analysis attacks require a large amount of power or current waveforms. However, the precision of these waveforms does not need to be very high. Then, with this data, the attacker will build a model or some hypothesis about the secret key information. Advanced data analysis techniques, such as statistical methods, normally in the form of computer softwares, will be used to reveal the key information. Differential power analysis can be performed in any algorithms that use the S-box with the exclusive OR of the segment key and some known data alpha as input. For a differential power analysis attack to be successful, the following conditions are needed. First, the attacker must know the crypto algorithm under attack. It is well known that the security of a cipher or a crypto system is based on how hard it is to break the secret key, not on which crypto algorithm the system uses. But in practice, knowing which crypto algorithm the system uses can be very, very helpful for the attackers. Second, as we have mentioned in the last slides, differential power analysis attacks need a large amount of power traces. This normally implies that the attacker will have physical control of the system for some amount of time to collect such data. Third, unlike the simple power analysis attacks that do not need much help from software tools, most of the differential power analysis attacks require some statistical analysis tools to study the data and extract the secret information. The two big advantages of differential power analysis attacks compared to simple power analysis are that they do not need to know the hardware and software implementation details of the crypto devices, and they do not need the power and the current waveforms to be very accurate either. Now we see some details about differential power analysis attacks, starting with the data collection phase. The algorithm here in the black box, or the key that is used in this algorithm, is the target of the differential power analysis attack. The attacker will run the algorithm with a piece of input data m sub I and to obtain output c sub I. Meanwhile, the power waveform Wi during the execution will be captured. The attacker will then repeat this process to collect more power waveforms W sub i's. Normally, from hundreds to hundreds of thousands of measurements might be needed for a successful differential power analysis attack. This number depends on the crypto system under attack and also the quality of the side channel information. After the data collection, now the attacker has a lot of triples of the input text m sub I, ciphertext c sub I, and the power or current waveforms w sub i's. Assuming that the attacker knows the crypto algorithm being targeted and wants to figure out the key only, let function f be the operation or transformation this algorithm is performing on the input data m with hidden secret key. The attacker can compute the output L sub I when the input M sub I is applied or plugged to the function f with any possible key value k. He then can select a bit position j in the output Li and let's call this bit L sub ij. The large amount of data the attacker has collected will then be partitioned into two disjoint, which means non-overlapping subset S sub 0 and S sub 1. In S sub 0, it has all the triplets of Mi, Ci, and Wi, where L sub ij is 0. And in Si, it has all the data where Lij has value 1 at the jth bit position. Then the attacker can compute the average waveform information in each of these two subsets, which is calculated here by summing them up and divided by the number of pieces of data in each of the sets. And then they can calculate the difference between these two average. We call them delta, and also we call them as the DPA value. Based on this value, the attacker can build a model, or they can do the hypothesis test to deduce the correct key. If an incorrect key k is used to compute the output L sub i's, the values of Li and the real output C of I will not have any correlation. Recall that the two subsets S0 and S1, they are partitioned based on the bit value of Lij. But the power waveform Wi's, they come from the real computation of Ci's. In this case, because Li's and Ci's, they are not correlated. Therefore, in each of these sets, when we compute the average, the power waveform collected will output 0, and those where when the output is 1. So when we do the average, we will have very similar values. So their difference, which is the DPA value, will be very close to 0. However, when the correct key k is used, the computed output L sub I and the real output C sub I should be the same. Therefore, the power waveforms Wi in the same subset should be similar, and the waveforms from different subsets should be different. This will result in a large gap between the average power for 0 and the average power or average current for 1. The difference is the delta or the DPA value. So we can locate the correct key with high probability by looking at the key values that cause peak values in DPA. This slide shows how how differential power analysis attacks breaks a 128-bit AES key, or 16 bytes. As described earlier, first, a large amount of input text M sub i's will be encrypted to generate the ciphertext C sub i's, and the power waveforms will be collected. Then for each byte k sub I, which has 8 bits, there will be 2 to the power 8 or 256 possible key values. We use each of them as the key to compute the output ciphertext L sub I, then do the partition of the collected power waveforms based on L sub I, and compute the DPA values. Because there are 16 bytes, so the total number of DPA values we have to compute will be 256 times 16, which is 4096. The following figure shows the result, where we can clearly see there are a few peaks. For example, the guess 1 here has the largest peak, which indicates that this most likely will be the correct key. It is non-trivial to compute the DPA value, given that the power waveforms we will have to collect may be in tens or hundreds of thousands. So doing DPA computation for 4096 times is not an easy task. However, this can lead us to break the 128 AES key. If we do the brute force search, the key space will be 2 to the power 128. This is much larger than 4096, which is only 2 to the power 12.